so this is the day 7 of Unit 2, lesson on multiplying matrices. So we started with a warm-up. So here's the warm-up. Pause the video, take a minute, do the warm-up, and then play to check your answers. So the first one, state the dimensions of each. A is a 3 by 2, 3 rows, 2 columns. B is a 2 by 2. C is a 1 by 3. And D is a 3 by 3. Number 2, find A32 and D13. A32 is equal to, I go to A, I go to the third row, second column, and that's -5. D13, I go to D, I go to the first row, third column, and that's a 5. A plus B. Well, looking at A, it's a 3 by 2, and B is a 2 by 2. So I see that they do not have the same dimensions, which means A plus B is not possible. Okay. So next thing we did was this problem. So this problem is referring back to the linear programming problem we did with Otto and the toys and the toy cars and trucks. And if you remember from that problem, we know that each car requires 4 wheels, 2 seats, and 1 gas tank, and each truck requires 6 wheels, 1 seat, and 3 gas tanks. So now we're being told that Bullseye wants 20 cars and 25 trucks, and J.C. Nichols wants 15 cars and 30 trucks. So we're supposed to use matrix multiplication to determine the parts needed to complete each order. Okay, now before we do that, just want to talk about why we're going to be doing that. So if you recall, when we did that linear programming problem, we made a long list of all the possibilities for numbers of cars and trucks that Otto could produce given the supplies in his storeroom. And if you remember, when we did that, to figure out if he had enough parts, we would take the number of cars, in this case 20, and we'd multiply it by the number of wheels needed per car. So 20 times 4. And then we'd do the same thing with the number of trucks, 25, and we'd multiply that by the number of wheels needed per truck, which was 6. And then that would give us a total for the number of wheels needed for that amount of cars and trucks, in this case 20 and 25. So the reason I know I'm going to be multiplying here is because that's how we did the problem before. We multiplied the number of cars times the number of wheels needed per car, and the number of trucks times the number of wheels needed per truck. So that's how we know that we're going to be multiplying. Now, we're going to use matrices to do that, again, because if this were a real life situation, we would have this toy maker would be selling to probably hundreds or thousands of stores, and they would be selling hundreds or thousands of toys, not just cars and trucks. So there's a need for matrices so we can put all those numbers in the matrix and then do the calculations just instantaneously all at once, rather than number crunching with all of those hundreds or thousands of numbers. Now, we're looking obviously at a real small example here, but the idea remains the same, the multiplication of matrices. So I'm going to take the information given, the number of cars and trucks, and I'm going to take the information given about the number of wheel seats and gas tanks required per car and per truck, and I'm going to put that into 2 matrices. So I'm going to start with the cars and the trucks and the cars and trucks for each store. So I'm going to put 20 and 25, 15 and 30 into a matrix. And I'm just going to label that matrix with what it represents. So the rows represent Bullseye, and the first row, and the second row represents J.C. Nichols. So I'm just going to label that. Column-wise, 20 and 15, those are the cars, and the 25 and 30, those are the trucks. So that's my first matrix. The other set of information is right here, the 4, the 2, the 1, the 6, 1, and the 3. So I'm going to put that, whoops, let me make a little bit more space here. So 4, then 2, then 1, 6, 1, and 3. And I'm going to put that in a matrix. And I'm going to label the rows and columns here as well. So the 4, 2, 1, those are for the car. And the 6, 1, 3, those are for the truck. The 4 and the 6, those are wheels. The 2 and the 1, those are seats. And the 1 and the 3, those are gas tanks. Okay. So now I have those two matrices. Now I know that I'm going to be multiplying. And what we need to decide is, first of all, sometimes multiplication is possible, sometimes it's not. And other times, the order makes a difference here. So I wrote these two in this order, but I have to check if multiplication is even possible in the order that I have them written. And if not, if I flip around the order, will that make a difference? With matrices, the order matters. So it's not like numbers. If I have 2 times 5, well, that's the same thing as 5 times 2. There, the order doesn't matter. With normal number multiplication, the order does not matter. But with matrices, the order does matter. You'll get a different result, or sometimes one order is not possible, and then flip it around, the other order is possible. So we need to check for that. The way that you check is by looking at the dimensions. So this is a 2 by 2. This is a 2 by 3. And the way that you check to see if the order is correct is by looking at the numbers that are on the inside when we have them written in that order. And we call those the inner dimensions. The inner dimensions must be equal in order for multiplication to be possible. And in this case, when I check that, I can see they are equal, so multiplication is possible. Now, had I, let's say, written these two matrices in the opposite order, the one here on the right first on the left and vice versa, then I'd have the 2 by 3 written first, and I'd have the 2 by 2 written second. And then when I check the inner dimensions, they're not equal. So I would realize that multiplication is not possible in that instance. Okay, not possible in that instance because the inner dimensions don't match. Okay, so I do have them in the order that I want to in order to be able to multiply them. If I had written them the opposite way first and realized that, then I would just check the order in the reverse, and I would see that it's possible in the way that I have it written here. So let me get that erased so we can continue working. So the other thing we want to talk about is we do have labels here. We have labels for the rows and labels for the columns. So that means I actually have a name for this matrix here on the left and this one on the right as well. So on the rows of the left matrix, I have stores. And on the columns of that left matrix, I have vehicles. So we could call this the store by vehicle matrix. The second matrix, we have the vehicles on the rows and we have the parts on the columns. So we could call that the vehicle by parts matrix. And not only should we check that the inner dimensions are equal in order for multiplication to be possible, but we should also check that the inner labels, in other words, the column labels for the first matrix have to match with the row labels for the second matrix. And if they don't, then you're going to have to adjust things. Like I could have set this up opposite, maybe putting the cars and trucks here as my rows and the stores as my columns. I may need to adjust that if I'm finding it's not lining up correctly or matching up. Here I have the vehicle matching with the vehicle, so I know that we have it lined up correctly. Again, if you don't have the same information here, you're going to have to adjust it and move things around until you get it right. So now I'm ready to multiply these. And I'm going to use the dimensions again. I'm going to look back here, 2 by 2 and 2 by 3. So to figure out what the dimensions of the product matrix are going to be, we look at the outer numbers or the outer dimensions. and 2 and 3, so a 2 by 3 matrix is going to be my product matrix. So I'm going to go ahead and make a 2 by 3 matrix. And I'm going to go ahead and fill in blanks to represent the different spots of my 2 by 3 matrix. And I'm also going to label the rows and the columns. Now, just like we did here with the dimensions, the numbers 2 by 3, the outer labels are going to be our labels for our product matrix. So I know this is going to be a store by parts matrix. And so I can go ahead and label the stores B and J. And I can go ahead and label the columns as the parts, which are the wheels, seats, and gas tanks. Okay. So now we're ready to start filling this in or multiplying the two matrices. So I'm looking to fill in this first blank here, which we know is the 1, 1 blank. Okay, so I'm just going to label that with its position. So if I'm thinking in this problem in terms of just common sense and what we would do if we hadn't set up matrices, I kind of already said that a minute ago. If I want 20 cars and 25 trucks, and I know that each car needs 4 wheels and each truck needs 6 wheels, then I can just use some common sense here, and these numbers are small enough that I could figure out the number of wheels needed to fill Bullseye's order without even using matrices. So, and that's what we're filling in right here is the wheels for Bullseye's order. So I know using common sense that I would take the number of cars times the number of wheels that are required per car, and I'd add to it the number of trucks times the number of wheels needed per truck. And I get 80 plus 150, which is 230. Okay. Now, that was using common sense and not using the matrices, but the point of this problem is to demonstrate how we multiply matrices, or the process that we use. So let me explain how I would do that if I wasn't just using common sense. So this blank that we are trying to fill in is the 1, 1 spot. Okay? 1 meaning row. So I look to the first row of the first matrix. And then 1 meaning column. So I look to the first column of the second matrix. And then notice what we did here. We did 20 times 4. Well, 20 is the number on the left, and 4 is the first number. When I'm looking top to bottom, it's the top number. So 20 times 4, and then I'm reading left to right and top to bottom. So 25 times 6, and then I add those. Okay, so that's how we'll fill in all of these. So if I don't have the story to go off of to help me, and I'm just trying to multiply matrices, I'm going to get this next blank, which is the 1, 2 blank. 1, 2 means first row and second column. So I will do 20 times 2, and I'm going to write this. This is my work. And I'm going to add 25 times 1. And 20 times 2 is 40, and 25 times 1 is 25. And when I add those, I'm getting 65. So we're going to continue on in the same fashion. This is the 1, 3 position. So I'm going to use the first row and the third column. So I'm going to multiply 20 times 1, and I'm going to multiply 25 times 3. And I'm getting 20 plus 75, which gives me 95. Okay, now we're going to label the numbers or the placements of the second row. So this is the second row, first column, the second row, second column, and the second row, third column. So 2, 1 means I'm now focusing on the second row, and I'm going back to this first column. So 15 times 4. And 30 times 6, 15 times 4 is 60, and 30 times 6 is 180, and 180 plus 60 is 240. Now the second row, second column. So 15 times 2 and 30 times 1, and that's 30 plus 30, which is 60. And lastly, 2, 3, second row, third column is 15 times 1 and 30 times 3 gives me 15 plus 90, which is 105. So this right here is my final answer. That's the product matrix. And you should also be able to interpret that. So if I ask something like, okay, well, what does the 65 represent? You would hopefully realize that that means the number of seats required to fill Bullseye's order. Or if I ask you what number represents the number of gas tanks needed for J.C. Nichols' order, you would hopefully realize that that number is 105. Okay, next we looked at multiplying matrices that don't have any labels. We don't have a story this time, we just need to multiply the matrices. And that sometimes happens. Sometimes you just have matrices with no labels, no story. So we're going to go ahead and try this one, CD. So CD, before I even write the matrices, I'm going to check their dimensions. So C is 1 by 3 and D is 3 by 3. So I'm checking in that order, C first, D second, the inner dimensions are the same, which means that multiplication is possible. So I'm going to go ahead and copy both of those matrices, -4, -1, 2, and I'm putting them, of course, in that order. And then D, 1, 0, 5, -2, 3, -1, 2, -4, 1. So now I'm going to go ahead and multiply. So we said that multiplication is possible. We also can see the dimensions are going to be 1 by 3. So I'm going to go ahead and make a 1 by 3, 1 row, 3 columns. And I'm going to go ahead and label those positions. So we have the first row, first column, the first row, second column, and the first row, third column. Okay, so I'm going to go ahead and begin by multiplying the first row, which is the entire matrix, times the first column. So I have -4 times 1, -1 times -2, and +2 times 2. So that gives me -4 plus 2 plus 4, which equals 2. Continuing on, 1, 2, first row, second column. So -4 times 0 plus -1 times 3 plus 2 times -4. Gives me 0 minus 3 minus 8, which is -11. And lastly, 1, 3, first row, third column. I'm doing -4 times 5, -1 times -1, and +2 times 1, which gives me -20 plus 1 plus 2, which equals -17. And that is my final product. Next one, we're going to find BC. So BC is a 2 by 2. Or B is a 2 by 2, I should say. C, we already said that's a 1 by 3. So in that order, 2 and 1 don't match up. So this is not possible, or you could say undefined. Not possible to multiply in that order. Okay. Next, we're going to find AB. So let me find the dimensions of A. That's a 3 by 2. And B, we already said, is a 2 by 2. So checking the inner dimensions, they're the same. And then I know the outer dimensions, 3 by 2, are going to be the dimensions of the product. So I'm going to go ahead and write my A matrix first. 1, 0, negative 2, 3, and 4, negative 5. And my B matrix second. And I'm going to go ahead and make a, we said 3 by 2. Matrix. And I'm going to figure out what belongs in each of those spots. So to help me, I'm going to label this as the first row, first column. So I'm going to use the first row and the first column. So I'm going to do 1 times negative 2, and I'm going to add on 0 times negative 1. So that gives me negative 2. Next, this is the first row, second column. So first row times the second column, 1 times 5 plus 0 times 8 gives me 5. Next, this is the second row, first column, 2, 1. So second row back to the first column. So that means negative 2 times negative 2, and then 3 times negative 1 gives me 4 minus 3, which is 1. Next, 2, 2, second row, second column. So negative 2 times 5, and then 3 times 8. So that's negative 10 plus 24, which is 14. Next, the third row, first column, comes from the third row and the first column. So 4 times negative 2, and negative 5 times negative, lost my place here, times negative 1 is negative 8 plus 5, which equals negative 3. Let me just check that. 4 times, whoops, I did that wrong. I was looking at the wrong thing here. We're doing the, I forgot which one I was doing. We are doing the third row, first column. Third row, first column. So 4 times negative 2 and negative 5 times negative 1. No, that's right. 4 times negative 2 and negative 5 times negative 1. Yes, I think that's good. So that is negative 8 plus 5, which is negative 3. Yep. No, I was correct. Okay. Thought I did that wrong. Now we're on the 3, 2 spot. So third row, second column is 4 times 5, and then negative 5 times 8 gives us 20 minus 40, which gives us negative 20. So my final result, that's kind of hard to see with all those labels, is negative 2, 5, 1, 14, negative 3, and negative 20. And that's my final result. Okay. All right, so homework for tonight is pages 19 through 21 in your Unit 2 packet.